All right, so yesterday we concluded the lesson dealing with the Euler parameters, which is a way of parameterizing the orientation of a body, of a rigid body in 3D space. As we already anticipated, there are actually several ways, several parameterizations which are possible in order to be able to describe the orientation of a body in the space. In fact, what we are going to do today, at least for part of the lecture, is going through two additional representations, okay? So the first one is called Rodriguez parameters. And then we will see also Euler's parameters, okay? And with respect to Euler's parameter, we will also see what we have already mentioned yesterday, the so-called gimbal lock problem, okay? Which in Italian is also called as blocco cardanico, okay? Have you ever heard of it? Blocco cardanico. Oh, my bad. What about home?
Professore, ci sente?
Have you ever heard of something called blocco cardanico? No? Ah, no, sorry, wait a minute, because we lost you since... okay, now we should be able to hear you back. Okay, can you please try again to say something from home?
Ci sente?
Yes, thanks.
Ok, adesso sì.
All right, so let's start with Rodriguez parameters. The difference with what we have seen yesterday, which were Euler's parameters, is that in this case we have only 3 parameters. And as we already saw, that's the minimum that we need, right? Because we need at least 3 parameters, because 3 have to be independent. Okay, so we can have even 7, 8, whatever, but then only 3 are independent. Okay, so the least, the smallest number that we need in order to be able to identify univocally the orientation of a body in space is 3. Okay, so 3 parameters. What are these 3 parameters? Well, if we recall our transformation matrix that was introduced as like so. It's actually 2. Okay, so we define this quantity here, gamma, which is a vector, has the vector v, which is the axis of rotation, it's a unit vector, as we already saw, times the tangent of theta divided by 2. So that, basically, we have that the components of this gamma vector are the 3 Rodriguez parameters. Okay, so the first Rodriguez parameter is called gamma 1, and is nothing less than v1 times the tangent of theta divided by 2. And in a very simple way, okay. Now, we already mentioned that there is a problem when we only use 3 parameters, which is the, as we said, the smallest number possible. And this problem is that we may encounter a problem of singularity. All right, so there may be some orientation which we are not able to describe when we only are using 3 parameters. Can you see this singularity here only using these 3 parameters? For what values of, for example, of the angle theta, can you guess we have a problem? Well, when we're going to have the singularity of the tangent.
Pi.
Yeah, well, not pi. Pi divided by 2, right? Plus minus. Plus minus pi divided by 2. Okay. For that, well, yeah. For the overall angle, for theta, of course, it's pi. Okay, so plus minus pi. So we're gonna stress this out. For theta plus minus pi. Okay. So when we are close to that, we are in trouble. Okay. So that's one of the cons of this method. There is a way we can implement to express the Rodriguez, so the matrix of transformation, the rotation matrix A, only in terms of the Rodriguez parameters, okay, which justifies the way they are defined. So because always one can wonder why they are defined like this, okay, we are going to see why. Because with this, with such definition, we will be able to express the matrix A in terms of these Rodriguez parameters. So kind of in a straightforward way. Let's see how. So let's see how to express A as a function of gamma. Okay? So first of all, we start from here, and we see that basically, let's take a look at this matrix. Okay? What we have to do is basically, first of all, express the sinus of theta and the sinus square of theta divided by 2, resorting to the parameters. Okay, this is the first thing that we have to do. So in terms of these quantities here on the bottom right part of the board. So let's start with the sinus of theta. So the sinus of theta is equal to, for trigonometric formula, and expressed as 2 times the sinus of theta divided by 2 times the cosinus of theta divided by 2, right? And then this, if we basically multiply and divide by the cosinus of theta divided by 2, this is 2 times the tangent of theta divided by 2 times cosinus squared of theta divided by 2. Okay, so I just multiplied and divided by cosinus of theta divided by 2. And this can be written as 2 times the tangent of theta divided by 2, which is basically this part here. And this, we put it, below. It's like 1 divided by cosinus squared of theta divided by 2. Right? So it's not nothing super fancy. And 1 over cosinus of squared of theta divided by 2 is the second. Okay? It's by definition the second. Second squared of theta divided by 2. And the second, again, can be expressed as always resorting to trigonometric formulae as 1 plus the tangent squared of theta divided by 2. Okay. Now, we have that for its definition, gamma transposed applied over gamma, which is the scalar product, as we said yesterday, is, by definition, the tangent squared of theta divided by 2. And this, we call it, by definition, gamma. Gamma without the underbar. So it's the module, okay? It's the value of the scalar product. It's a scalar quantity. Sorry, gamma squared. So this implies that eventually, if we take into account all that we have written above, the sinus of theta can be written as 2 the tangent of theta divided by 2, all of it divided by 1 plus gamma squared. Okay, so this is the first, let's say, result that we were searching for. Okay, because we have expressed the sinus in terms of the gammas. Okay. Now, what about the sinus squared? Let's see. So the sinus of theta divided by 2, again, if you recall the definition, of the trigonometric formula, can be written as the sinus of theta divided by 2, the cosinus of theta divided by 2. You see, it's just the same formula that you have written before, because you have that the sinus is equal to the sinus of theta divided by 2 times 2 cosinus of theta divided by 2. It's just the same. Now, resorting to the definition of the sinus, okay, that we have just done before, we can rewrite this as 2 times the tangent of theta divided by 2 over 1 plus gamma squared times, well, what's below the fraction. So this and this we can basically remove. Now what we do is basically multiply both, all right, both the sides of this equation, so the left and the right hand side, by the sinus of theta divided by 2. So this means that the sinus of theta divided by 2 squared is equal to the tangent of theta divided by 2 over 1 plus gamma squared. Now I should basically multiply also the right-hand side by sinus of theta divided by 2, right? If I multiply here on the left by sinus of theta divided by 2, I have sinus squared. I do the same on the right, okay? If I do the same on the right, what do I get? It's the sinus of theta divided by 2. Okay, let's do all the things, right? And this is a tangent, right? Again, so why? I'm just multiplying. Yeah. So tangent of theta divided by 2 squared over 1 plus gamma squared. Okay. So substituting in A, you can write the following. Plus 2 over 1 plus gamma squared, which multiplies ni tilde times the tangent of theta divided by 2 plus what we have called basically v squared times the tangent of theta divided by 2 squared. Okay. I just substituted the sinus and the sinus squared of theta divided by 2, okay, in our definition of A. That's all I did. Okay. Now we define gamma tilde as mi tilde times the tangent of theta divided by 2. And therefore, our A matrix becomes the identity matrix plus 2 over 1 plus gamma squared, which multiplies gamma plus gamma tilde squared. Okay. Where you see, why did I define, my gamma tilde matrix like this? Because resorting to the definition of the Rodriguez parameter that we started at the very beginning of this calculation, we have that gamma tilde is always a skew matrix, which is done like this: gamma 3, 0, gamma 2, gamma 3, 0, minus gamma 1, minus gamma 2, gamma 1, 0. And these streams from the definition that we have done early on of the Rodriguez parameters here. See? Okay, from here, from this definition here. So resorting to that, and that basically explains why the Rodriguez parameters are defined like that, because if we define them like that, we can rewrite very simply the rotation matrix like this. Okay. Okay. All right. Let's see. We can, of course, at this point, try to establish a relationship between the Rodriguez parameters and the Euler's parameters that we have defined yesterday. Okay? Of course, since they are used to define the same thing, which is the rotation matrix, or in general, more abstractly, the orientation of the body, of course, there must be some connection between them, right? They must be related the one to the other somehow. Well, let's see. So from Euler to Rodriguez. Parameters. Oops. So we saw that Euler parameter, sorry, the Rodriguez parameters I, actually that's actually the converse. Yeah. Sorry, it's actually the other way around. We will do also the same thing, in fact, but okay. So Rodriguez parameters gamma I is basically, as we have defined it, vi times the tangent of theta divided by 2. And this can, of course, be written as the sinus of theta divided by 2 divided by the cosinus of theta divided by 2. And you see, this first thing here is what? This is Euler's parameter that we have defined yesterday. So this is basically theta I, while the one below is theta 0. So super straightforward. Now, to do the opposite, so to pass from Euler's to Rodriguez, we have to make some more steps first. So 2, now it's what I actually wrote before, is from Euler's. Okay. Well, from the development, the simple the mathematical development that we have done before, we can write that the cosinus squared of theta divided by 2 is 1 over 1 plus gamma squared. Okay. Now, this means that if we apply the square root to both, we actually have what? This is theta 0, and this is 1 over 1 plus gamma squared. So, resorting to what we have demonstrated just in the previous page, like here, we have that theta I is what? Is equal to gamma I divided by 1 plus gamma squared, okay? This comes from here, right? It's just the converse. If I try to explain here from this last, theta I is equal to gamma 0 multiplied by gamma I. But gamma 0, we saw it's this quantity, so this demonstrates basically the thesis. All right, so these are Rodriguez parameters. 3 parameters instead of 4. And they do suffer a problem of singularity. Okay. Now we will see another parameterization, which is called the Euler angle. And we will see that they actually suffer another problem additionally to singularity, they also have another problem which is called gimbal problem. So, and at that point is when I would like to show you the video. So, it's 3 parameters. So, what is the idea behind Euler's angles? Well, the idea behind Euler's angles is the following. So you see, if you want to describe, a rotation, a final orientation of your local frame, okay, you can always think of it as a succession of 3 rotations. Okay, so meaning that you eventually end up in the orientation of the frame that you want to describe as a sequence of 3 successive rotations. So that's the idea behind Euler's angles. In fact, this comes from Euler's mind to describe how the gimbal, the gyroscope, in fact, works. You can see it from here. So this is basically a very basic image of the gyroscope. You see? Basically, you have 3 circles, one inside the other. Each one has, in theory, an independent axis of rotation about which the circle can rotate. And then this means that the final orientation of the object which is inside can be described physically, this is physically really understandable, as a succession of 3 rotations, okay, of these 3 circles which are one inside the other, okay, and each one can spin about one axis, okay. So we have another gimbal, an inner gimbal, and then there is the object which can spin, okay. And in fact, this triangle of rotation, angle of rotations, are typically called as the nutation, the spin, and the precession. That's something which is super well known. So the first thing that we have to hold in mind is that the succession of the rotation is not defined a priori, meaning that the axis about which I will describe the 3 rotations, I mean, you can choose them as long as they are independent. So they don't have to be parallel. That's all. Okay. But in principle, you can choose them as you want. Okay. So for example, let's consider a succession of 3 rotations. A first rotation phi, which brings the local frame, which is initially coinciding, okay, with the inertial frame, in a new position through a rotation about the axis x3. Okay, so we have x3, b1, b2, and b3, and x1, x2, x3. Initially, they coincide. Then you have a rotation of an angle phi about the angle x3, and so you reach the intermediate orientation, which is defined by the axis x1, x2, and x3. All right. Then what you do is rotate again your frame about the axis x1 of an angle psi. Okay, and this brings you your frame into the second intermediate configuration, which here we have identified by the angle eta1, the axis eta1, eta2, and eta3. All right. Then the last rotation is about the axis eta3 of an angle phi. Okay. And this brings you to the final configuration, which is B1, B2, and B3, the one that you wanted to describe. Okay? So it's quite easy. So all of it is very nice. Let's see how we can actually describe this from a mathematical point of view. So in this case, the succession of the rotation, of the axis of rotation that we are taking into account is 3, because it is x1, the first axis of rotation. So it's 3, 1, because the second axis of rotation is xe1, sorry. And then, again, 3. See? So the sequence of rotation axis is arbitrary. We choose 3, 1, 3. But there are others possible, okay? How many? Well, all the couples, all the triplets, in fact, that can be formed by an inversion of these, these three subscripts, 1, 2, and 3. So the first rotation phi. Well, we have that the axis xi, the general axis xi, which can be xi1, xi2, and xi3, must be obtained as a matrix, a rotation matrix, applied over the axis xi, right? So I apply this rotation over the axis xi, and I should obtain Ci, right? Where this d is a function of the psi. Well, I think it's quite straightforward to know how this d is actually structured, no? We will actually call this as, for example, d1, because it's the first rotation, so d1. So d1 has a very simple structure. So it's a rotation matrix in the 3D space about an axis which is x3. So I would say, if you agree, that we have something like this, first of all. No? Because the axis of rotation, the plane of rotation is the plane x1, x2, right? But please note that here, this is not something similar to the matrix A. Why? Because A, and please note this thing, which is super important. A acts on quantities which are expressed in the local frame and gives you something which is expressed in the inertial frame, right? If you remember, A, the transformation matrix A, operates over R0 over bar and gives you R0. So it operates on something which lives in the local frame and outputs something which lives in the inertial frame. Okay. This instead is the opposite. It operates, this matrix D1, on something that lives in the inertial frame and outputs something which lives in the local frame. Okay? So that's why, in fact, this matrix D has this form: cosinus of phi, sinus of phi, minus sinus of phi, cosinus of phi. Okay? All right. Now, we do the same thing for the second rotation. Second rotation. Psi. Well, psi, as we saw, gives something like the vector eta I as a rotation d2 applied over the xi, right? But this time it's a rotation about the axis 1. So d2 will be something like this. Remember, it's about the axis xi1, right? So we have something like this: 1, 0, 0, 0, 0, right? Because the axis of rotation is 1, xi1. And then cosinus of psi, sinus of psi, minus sinus of psi, cosinus of psi. Yeah? So third rotation in a very similar way. Of the angle E. Well, this time you eventually have the axis that you wanted, BI, is D3 applied over eta I. This time, if you recall, since we are implementing a rotation sequence 3-1-3, again, the axis of rotation is the third axis of the triplet. That's to say eta 3. So we will have again something of this. Okay. Now, if we express if we put together all these three formulas, okay, we start from the last one, okay, in which we express the BI with respect to the eta I. But the eta I in the second formula can be expressed in terms of the xi, and the xi in terms of the inertial frame. So we have the BI is what? D3 applied over D2 applied over D1 applied over xi. Now, this actually goes in the direction of what I was telling you before. That's to say, remember that the matrix A, the rotation matrix, transformation matrix, operates over quantities that live in the local frame and outputs, gives you back something in the inertial frame. While here, you see we have something that operates in the inertial frame and gives you something in the local frame. So we can write that this is just our A to the -1. right? Does this confuses you? No, right? Again, so that xi must be equal to a applied over something that lives in the local frame, right? So our A is what? Is D3 times D2 times D1 to the minus 1, right? From the previous formula. And this way we get, this way we get the final A. And it is quite important at this point to see how this A is actually structured. It takes some time, but it's important. So if we try to actually execute this calculus, we get something like this. Let me just, in fact, this will take a lot of time, so let's do it on the final configuration. Sorry. So let's do like this. So this, so phi, psi, and phi are called Euler's angles. Associated to the 3-1-3 sequence. Okay? And let's say the interaction between Euler's angles and Euler's parameters is the following. Okay, from Euler's angles to Euler's parameters. Well, our theta 0 can be written as, this can be demonstrated as the cosinus of c divided by 2 times the cosinus of phi plus theta divided by 2, and this is 1. Then we have theta 1, which is the sinus of theta divided by 2 times the cosinus of phi minus theta divided by 2 is the sinus of phi divided by 2 times the sinus of times the cosinus of c divided by 2 times the sinus of phi plus theta divided by 2. Okay? So this is the first the first passage. While the second is from Euler's parameters to Euler's angles so C is cosinus to the minus 1 of 2 times theta 0 squared plus theta 3 squared minus 1. I'm just, writing them down because they can be useful to you at a certain point, but all of this can be, of course, derived from what we have seen. And I won't be asking you to the exam to derive this part, this formula, because you can find them here or in other books. This is minus 2. And then phi is the sorry. Okay, now, all of this was quite tedious, but we now come to the problem that I was hinting at the beginning of the lesson, which is the gimbal lock problem, okay? So, another very, very popular sequence to describe the orientation, the final orientation of a frame is not the 3-1-3, which is very popular in the aerospace field, but also the 1-2-3. Okay. So let's see the sequence. Which is called 1-2-3. That's to say, phi about the axis x1 plus we have c on the axis, about the axis x2, sorry, plus phi about the axis x3, okay? So the 3-1-3 that we saw before is actually the original one, the one that was implemented by Euler to describe the gyroscope, okay? This one here is actually something very popular in the aerospace. Now, and that's the most tedious part of today's lecture, unfortunately, let me write the A matrix for the 1-2-3 sequence. Because if we do that, we will see that there is something very important to see. Okay. Let's start. So these are the first three. This is the second column. I think I've used too much space here, but okay. Okay. And at last, okay, now, if you take a look at this, allow me to move this out. You may notice something. What happens if C is equal to pi divided by 2? Can you see? Well, if pi is divided if C in this case is equal to pi divided by 2, then A becomes like this. A 1, 2, 3 becomes this 0, 0, 1, you see? Minus cosinus of phi, sinus of phi, sinus of phi, I know it's a little bit tedious, but this is something that we have to go through at least one time. and then 0 and 0. Okay? So why did I do all of this? Because now if you take a look at the terms which are not 1 or 0, they can be grouped. They can be grouped like this. So C is always equal to pi divided by 2. We can rewrite A like this, very simply, 0, 0, 1, minus sinus of what? Phi plus theta, minus cosinus of phi plus theta, cosinus of phi plus theta, minus sinus, sorry, this is like this, of phi plus theta. Okay. So what I'm saying here is that if you rearrange this matrix here, the second one, this is just the sum of cosinus of, or sum of sinus of two angles. So this one here, the one on the bottom, is exactly the one that you see here. Can you see what's the point on this? The point on this is that, recapping, is that if I put psi equal to pi divided by 2, then now if I change phi or theta within this sinus or cosinus, I obtain exactly the same effect, right? So if I change phi or theta inside, it doesn't really matter. And that's a problem. That's a big problem. Because it means that first, I had 3 independent axes of rotations. Each one was referring to one of the 3 Euler's angles. And through this independence of the axis, you see, setting the wanted value of these 3 angles, I could achieve any kind of I could describe any kind of orientation. Now, if I set phi or psi inside this parenthesis here in this matrix, I obtain the same exact thing, meaning that the axis of rotation referring to phi of psi within these functions are parallel. If I rotate, so if I rotate of an angle phi equal to, I don't know, whatever, let's call it beta, or phi equal to beta, it's the same. This means that the axis of rotation associated to phi and psi are become parallel, right? That's the only, occasion in which if you rotate of the same amount two angles and you obtain the same thing in terms of configuration of the rotation matrix, it just can mean that the two axes of rotation, in this case, it would be C1 and eta 3, they have become parallel. And again, this is a problem because I can no longer describe any possible orientation, because I can basically do this. If I define as alpha equal to phi plus c, A becomes what we have seen, right? It becomes 0 minus sinus of alpha minus cosinus of alpha, 0 cosinus of alpha minus sinus of alpha, 0, sorry, 1, 0, 0. So you see, I no longer have 3 parameters, but once I have set psi equal to p divided by pi divided by 2, I'm only left with one parameter, basically alpha. If I rotate of an angle phi or theta here, it doesn't matter anymore. So I lost, what I'm saying is that I'm lost 1 degree of control of my orientation, okay? And this condition happens when I approach the value of psi equal to p divided by pi divided by 2. This condition is called gimbal lock. Gimbal lock, okay? And it's a supercritic condition. And we will see now why. And it's called gimbal lock because, as you can see, there is no way now, mathematically speaking, to go back to the previous condition in which I had all of 3 degrees of rotations. And of course, this condition here the value of psi depends on the sequence that we define. So in this case, we have defined the sequence 1, 2, 3, and so psi is equal to pi divided by 2, for which we have gimbal lock. For example, for the first one that we have defined, for the sequence 3, 2, 3, 1, 3, it's p, I think it's 0, okay, for which we have that. So it's the condition specific for the sequence 1, 2, 3. For the other one, as I said, for 3, 1, 3, I think it's 0. All right, so that was somehow a little bit tedious. Now I wanted to something from home.
Professor, a quick question.
Yes.
What would be the procedure to recover from gimbal lock?
I'm sorry?
What could be a procedure to recover from a gimbal lock?
We will see it now. We'll see now. You have to do it manually. And when I say manually, it means that this parameterization was actually used, as I was mentioning yesterday, in various spacecraft. And once it's lost, so once you get into gimbal lock, you have to manually reset your instrument using the fixed stars as mean of orientation. We will see that right now, hopefully in a nice way. I have a video to show you first. But we lost the connection with Owen, I guess. Yeah, it's either this one or the. So, guys, from home, if I wanted to show you a video, but apparently it's either the video or the possibility for you to talk. All right. So I will try to share the video right now, but before actually starting the video, I would like from you a confirmation that you can actually hear, okay, a written one on the chat of the Microsoft Teams platform, okay? So let's do it. Yeah, you see, it's just. Mi sentite se parlo? Vedete lo schermo? Okay. Okay. I will try to play now the video, and let's see if it works. Okay, if you can actually listen to the audio at least from home. I will try to. You should be able to do it anyway, at least through my microphone. So let me put the microphone close to the speaker. Okay, let's see.
The work this gimbal machine shows us. Each part is linked to one another, so when the parts slide around, we can see how the rotations are passed on. By spinning each of the machine's 3 arms, we can rotate the jet into any angle. But notice when the jet points up, how 2 of the circular arms up.
You see, so these 3 circles that you see here in this gimbal machine are actually the 3 circles of the gimbal, of the gyroscope that I showed you before, right? And so as you can see, each one of these circles can rotate about an axis, okay, which are the axes that we have defined previously in our mathematical formulation, all right? As you can see, as you rotate these 3 circles, one inside the other, you can obtain every possible orientation, in this case, of an airplane, okay? All right? But now, pay attention to what has happened. Now, you see that there are 2 circles, the outer one and the most inner one, okay, which are on the same plane, okay? So it means that you see, we have 2 of the axes of rotation which have become parallel, okay? So the inner one here, which goes through the airplane, and then the other one of the other one, which basically is parallel. It's not easy to see, but it's parallel. Okay, it goes like this.
This is exactly the same effect of gimbal lock, causing 2 circular arms to rotate on the same plane. Let's make this.
You see, what happens is that it is trying to rotate 2 circles, but you obtain exactly the same effect. It always stays in the same plane. And that's exactly what we have seen through the matrices. When we have phi and theta, and then we define alpha as the sum of the 2. You have basically lost one parameter to orientate correctly your spacecraft. Okay?
In a hierarchical system. To demonstrate, we'll grab some torus objects. They can represent each axis. Green will represent Y, X will be red, and Z blue. So altogether we have 3 toruses and an arrow object. Let's parent them together. X to Y, Z to X, and the arrow to Z.
So what he's doing here right now, when he's talking about coupling the different circles, this equals to choosing the sequence of the axis of rotation that we have said during the lesson before. So choosing how these 3 angles pair the one with the other, so which one is the inner one, which one is the outer one, basically equals to the choice of the axis of rotation. For example, first, in the very first part of the lesson, we have chosen 3, 1, 3, but then eventually we also have shown the 1, 2, 3 rotation. So this is what he's talking about in this part.
This is going to mimic a rotation order of y, then x, then z. The y, or green torus, is at the top of our hierarchy. So in this parent structure, everything rotates with it. Z, on the other hand, affects the arrow, because it's at the bottom of the hierarchy, or the last axis in the rotation order. X is second in the rotation order, so it'll affect Z below. And see how Y stays still, because it's at the top of the hierarchy.
Here it's just showing how it works, okay, how it rotates.
Here's where things start to get interesting. If we continue to rotate X in the middle of the hierarchy, it'll cause Y and Z to align.
Okay.
Here, this rotation order hits gimbal lock when two axes align.
That's gimbal lock, you see? Two axes are aligned.
If we're animating and our next step is to turn the arrow down, there's a problem because there's no axis to turn on. Here's the missing axis in grey. It's always...
So the motion that we was showing before, now in grey, is the motion that you are no longer able to control, that you missed. Okay? So this is important because if you build an orientation system of a spacecraft based on this as they did, and you get into this condition, then you have a problem. You have an instability problem because you are no longer able, your system, for example, if you have a propulsion system which is related, which is associated to your altitude system control, well, in this case, the spacecraft doesn't know anymore how it is oriented in space. And so how to actually direct all, for example, the thrust or forces. Okay, that's a problem. And from here you get the instability issue.
To rotate our arrow into any new rotation, but we'll have to rotate all three axes to achieve it. Let's undo this and rotate all axes at once.
You see, now what he has done to exit from the gimbal lock position, from the gimbal lock condition, sorry, is to rotate all the axes at once. But this has a cost, and if we see now what it is.
Notice how the arrow doesn't rotate in a straight direction. Instead, it moves in an unexpected arc. This is the cause of gimbal problems in animation, because the object can move unexpectedly in between keyframes.
Okay, so it means that once you make the rotation, all three of them at once, the object will move in a way which is not expected. You see, you look at the trajectory in yellow. It doesn't follow a circle anymore, because this should be the path followed by the top of the arrow, the tip of the arrow, should be a sequence of arcs, okay, as an effect of the three sequence of rotations. But if you rotate the three angles all at once, and this is what you do when you have to recalibrate it or manually the system, you go in an unexpected region of motion, okay, which is this one yellow here, which is not expected, and this is instability. This like all instability. Okay.
A solution is to use a different parenting structure. This will change the arrow's rotation order. Our new order will be Y first, then Z, then X.
What he's saying now is that basically you are adopting another sequence. Okay? If you want to describe that condition, the one in which the spacecraft is pointing upward, okay, on top, without actually falling into the gimbal lock problem, you have to change the sequence so that the angle that gives you problem is different from it. Okay?
In our new hierarchy, Y is still the parent, but X and Z have been swapped. Now we can rotate the object without hitting gimbal lock.
See?
In between, the arrow rotates as expected.
See?
But the gimbal problem doesn't go away, it just changes. With Euler, gimbal lock will...
I don't know if you saw that, but now the path is the one that we expect is an arc, right? But now it's saying what we have said already, that the gimbal lock product doesn't go away, it just has moved to another angle. Okay, see. Look at this.
Occur in some situation. There's just no way around it. In this example, gimbal lock still happens by turning the z-axis 90 degrees to cause the x and y-axis to align. In another parent structure, the rotate order might be z first, then y, then x. Now gimbal lock occurs when the y-axis rotates 90 degrees.
Then you go again, you see?
Altogether, there are 6 parenting combinations to choose from. In each case, gimbal lock occurs on the axis of the parent when the middle axis is rotated too far.
Each sequence has its weak point.
The work. This.
Okay, that's the same video. Let's go try to restore. So I hope that you could actually listen to and watch the video from home. Just a second. Can you confirm that you actually were able to look at to watch the video?
Sí, prof.
Okay, okay, nice. So now we have 5 minutes left, and we can either go through the properties of the rotation matrix or watch another video. And I say that we will watch another video because it's a fun one. This one is actually a very famous one, and it's one where you, if you listen to the dialogues of the people, of the actors within the movie, you will listen to the word gimbal lock. Okay. Let's see if you will be able to get which movie we're talking about. It's a very famous one, and this relates to a condition which actually happened in reality. Okay. And that's why we have to really be careful when we deal with gimbal lock. All right, again, from home, now you're disconnected. Huh? That's the explosion due to the gas. So for those of you who don't know about this, the astronauts of the Apollo 13 had an issue regarding the explosion of the basically one of the oxygen tanks, which lost pressure, and the other one was also was actually keep on losing air in space. And basically they were eventually forced to enter into the LEM, which was the lunar entering module, which was a module defined only to enter and to land on Moon, because this was, of course, one of the missions which aimed at landing again on Moon. But eventually they were not able to do so because they were losing oxygen, so they forced the astronaut to pass from the CMS, so the service module, to the lunar entry module, and they never actually landed on the Moon, and they were able to get all the astronauts back, basically making a tour of the Moon and reaching what is still the record of the largest distance of a human being has ever experienced it from Earth. Okay, the longest, the farthest away a human being has ever been from Earth. Okay, well, what actually matters to us in this part is that this explosion basically caused the spacecraft lose its control, its orientation, and they basically approach the region of the gimbal lock, which would have basically prevented them to control again the orientation of the spacecraft. Okay, so I'm not sure if this is the first part or the last part of the video. At one point, the astronauts will start yelling one to the other, "Look at the gimbal lock! Look at the gimbal lock!" Okay, because they don't want to lose also, on top of all the problems that they have, also the possibility to reorient the spacecraft. And this is something that actually happened to another mission, the Apollo 11. The Apollo 11, they fell into the gimbal lock directly. And to exit, as I was saying, they had to manually reorientate the axis of the rotation with respect to the reference frame given by the fixed stars. Okay. That's just an overview for the next couple of minutes.
Hey, we've got a problem here. What did you do? Nothing. I steered the tanks. Whoa. Hey. This is Houston. Say again, please.
Houston, we have a problem. We have a main bus being undervolt. We've got a lot of thruster activity here, Houston. Now. Just went offline. Oh, there's another master alarm, Houston.
I'm checking the quad.
Christ, there's no repress valve.
Maybe it's in quad.
We've got a computer restart.
I'm going to reconfigure the RCS.
We've got a baseline fire.
Doesn't make any sense.
We've got multiple caution and warning, Houston. We've got a reset to restart.
All right, I'm going to SDS. Jesus. Flight, the heart rates are skyrocketing.
Econ, what's your data telling you?
O2, tank 2, not reading at all. Tank 1 is at 725 psi and falling. Fuel cells 1 and 3 are, what's going on here? Flight, let me get back to you. Flight GNC? Flight, they're all over the place. They keep going close to gimbal lock. I keep losing radios.
Did you get that? They say if they keep on, let's say, having this problem, they will fall into gimbal lock. Okay? All right, so.
Their antenna must be 22. They're going to have to do it manually.
One at a time, people. One at a time. One at a time. Ecom, is this an instrumentation problem, or are we looking at real power loss here?
It's reading a quadruple failure. That can't happen. It's got to be instrumentation.
Let's get that hatch button. The limb might have been hit by a meteor.
Yep. The tunnel's really torquing with all Houston, we got a pretty large bang there associated with a master alarm. Ship's main bus A. Main bus A undervolt? Houston, we have a main bus A undervolt now too. It's reading 25 and a half. Main bus B is reading SIP right now. We got a wicked shimmy up here.
Econ TNC, these guys are talking about bangs and shimmies up there. Doesn't sound like instrumentation to me.
You get this half the steel.
Just stow it. If we've been hit by a meteor, we'd be dead by now. They're going to try to get us out of this alert.
Okay, they thought at first that they were being hit by a meteor. And instead it was an explosion attack.
Bud, did you say switch to Omni Bravo? Roger, and the signal strength on the high
Finding me. What's the story here, Jack? We keep flooding with gimbal up.
You see that one? That was the MIU. The MIU, so basically the unit which was used to monitor the altitude, okay, the orientation, and he was basically approaching the gimbal lock.
You get this half the steel.
Just stow it. If we've been hit by a meteor, we'd be dead by now. They're going to try to get us out of this alert.
You're in the mud. Did you say switch to Omni Bravo? Roger, and the signal strength on the high
Finding me. What's the story here, Jack? We keep flooding with gimbal lock.
So you saw basically they lost complete control, and as basically all the systems, for example, the power unit and the thrust, the propulsion, they are all linked to the altitude control system. You saw that there are thrusts, let's say, expulsion of gases in order to be able to maintain the orientation, but this is not correct. Okay. So I'm afraid that that's the end for today. But okay. So this issue that we see that sometimes can seem to be only happening on your notes, they actually cause a lot of trouble in real life. Okay, so they are important. Okay. All right. So this is it, guys. And if you do not have any other additional question, I would end here the lesson. Just a second. Just a second. So I would stop the record here.